In this example problem, we analyze a model rocket launching off the ground. They give you the mass of the rocket and then some engine specs that we're going to analyze and start to apply the concepts of Newton's second law, F equals ma, and also some concepts of momentum, where we see that momentum is mass times velocity. And more importantly, impulse being related to force and the time that that force is applied. All right, so let's look at the rocket here. It's always helpful to kind of draw a picture here. We're going to have the rocket on the launch stand. Right, and it's going to take off, right? It's going to be accelerating upwards. There's going to be forces on that rocket. We'll think about a free body diagram. And in this case, we're looking for the minimum engine thrust needed for liftoff here, right? So if we're going to be lifting off, then what's that free body diagram going to look like? Well, let's look at what happens when it's just sitting at rest. So I'm going to take this original picture here, and I'm going to draw the forces of it when it's at rest. Well, we're going to have its weight, Fg. And we're going to be sitting here on the surface, and that surface is going to push back. That's what's going to happen when we get a little bit of, when we have no engine thrust happening here. The force of gravity is equal to the normal force. And so if it was sitting on a scale, it would read its normal weight. But what happens when you start adding some thrust from the engine? Well, that engine is going to be applying an upward force. Let's call that the thrust force. Well, if we apply an upward thrust force, now we begin to accelerate, right? However, that's initially not going to overcome all of the gravitational force, right? So we need to have more thrust than gravity. If I had that much thrust force, you can imagine that the scale on the ground would just read less, and those two upward arrows would equal Fg. But I'd still be on the ground. As long as Fn exists, then I'm still on the ground. So if I need to lift off, well, at liftoff, the normal force is going to have to be 0. We can't be on the surface anymore, right? So if I shrink the normal force a little bit more, well, then that means I must have had a little bit more thrust force. So that rocket engine's getting a little bit bigger, but it's still not big enough to overcome Fg. Well, when we get to that minimum thrust at takeoff, well, that's going to occur when the normal force goes away, and we're going to have the thrust force equaling the force of gravity, right? So for scenario A, we know that we are accelerating upwards, right? And at liftoff, the thrust force is equal to the force due to gravity, right? So if we have that minimum, then the scale would read 0 and we're ready to take off. So what is that thrust force? Well, we better know what Fg is. And we know that to find Fg, you always take the mass of the object times the acceleration due to gravity. And so that's the force we need to overcome. Well, the mass of our object, they tell us, is 45 grams. Mass is 45 grams, but be careful, our standard is in kilograms. So we're going to convert this to kilograms. Grams to kilograms, right? There are 10 to the third grams in 1 kilogram. Right? So really we're going to be dividing by 1,000. And so my mass is 0.045 kilograms. And we know that the acceleration due to gravity is downward at 9.8 meters per second squared. Right? And so I know that the force of gravity is going to be 0.045 kilograms times the acceleration due to gravity, meters per second squared. And so I'm going to take 0.045 and multiply by 9.8, and I get the weight, which is 0.441 newtons. 0.441 newtons. That is in the downward direction. And if gravity is 0.441 newtons down, well, then the thrust better be 0.44 newtons up. So I know that the thrust force or the applied force of the engine has got to be upward at 0.441 newtons, right? So this is how we find the minimum thrust for the engine, right? So as long as we have about a half a newton, this thing's going to take off. But we want to do a lot more than that. We want this thing to fly high in the air, right? And that's what the engine provides, right? So let's look at scenario B and figure out what we got here. So what we're going to have is a bigger thrust force. Well, how much thrust does the engine provide? Well, they tell us something about the engine's impulse, right? We know that the impulse, J, of the engine is 2.9 Newton seconds. They also tell you the time of the engine firing is 0.7 seconds, right? So that impulse applied over a period of time is going to equate to some amount of force or thrust from the engine, right? So how do we find that? We want to know that engine thrust force. Well, how do we relate those values? Well, let's look at our equations, right? Impulse is simply force times time, right? So when I wrote down our variables, we know that impulse is equal to force times time. And therefore, if I solve for the force of thrust from the engine is just going to be the impulse divided by the time, right? So when I evaluate, I know that the thrust force is going to be 2.9 Newton seconds divided by 0.7 seconds. Look what happens to our units here when I do this. The seconds cancel, and you get units of newtons. Well, there you go. That's a force unit. So if I take 2.9 divided by 0.7, I get 4.14 newtons of thrust. So 4.14 newtons is the amount of thrust force that this engine can provide, right? So we need 0.441 to get off the ground. Well, this is going to give us 4.14. So we have plenty to get off the ground, right? However, what is the net force overall, right, of the rocket at liftoff? Well, let's draw this free body diagram now. And this rocket at liftoff still has FG. But now we have this big force of thrust that's upward, right? And so we know that if I want to sum the forces, the net force is simply the thrust force. Get my colors right here. The force of thrust plus the force of gravity. Now, again, this is where signs come into play, right? We know that the net force would be equal to the upward thrust force, positive 4.14 newtons, plus the downward gravitational force, which we found to be 0.441 newtons, right? That was the minimum thrust needed. So we knew FG already. That hasn't changed. But now we know how much thrust there is. And so if we're trying to find the net force, we just add them up. And so if I take 4.41 and subtract 0.441, I get the net force of 3.7. The sum of all the forces is 3.7 newtons upward, right? So now we know the net force on this rocket is 3.7 newtons. So what can we do with that? Well, now we can figure out the acceleration of the rocket at liftoff. If this thing is got a net force that's up, well, we can use that and Newton's second law, which tells you that the net force is what causes the acceleration. And we know that the net force is upward at 3.7 newtons. We know the mass is, from what we found before, 0.045 kilograms. And we can calculate our acceleration. So if I take 3.7 and I divide by 0.045, I would get the acceleration of the rocket, 82.26. Let's call it 82.3 meters per second squared. It'll be a positive value. Of course it will be, because we're accelerating upwards when we get an imbalance upwards. So I expect 82.3 to be my acceleration. Pretty big acceleration, right? If I was falling, it would be at 9.8 downward. So this is multiples of gravity upwards. This thing's going to really lift off quickly in that first, 0.7 seconds. All right, and then let's read the last part. As the rocket gains velocity, air resistance now becomes a factor, right? So right at the instant it leaves the ground, air is not an issue, but as you start pushing through air, it's pushing down. It's another force acting on the rocket. And they tell you, assuming the average drag, remember, it's going to change as you get faster and faster. So let's just simplify and say there's an average amount of drag force on this rocket that's going to affect how it can accelerate, right? This acceleration we just found is at the instant of liftoff, but then it's going to go faster and faster and faster. So let's look at scenario D or E rather, and let's draw the free body diagram of the rocket, which still has gravity acting down, Fg. It's got this large engine thrust, big arrow up, and now we have this extra arrow, right? We've got drag, right? So I'm going to draw a little drag arrow. Let's call it force of air, right? We can call it force of drag, maybe FD, right? It's a third arrow on our free body diagram, right? This thing is still accelerating upwards though, right? There's still an upward acceleration. The net force should be upwards because this thing's taken off, but it's just not accelerating as much. It should be smaller than the other one. Well, they want to know what is that new acceleration, right? And so we can identify the things we know, right? We know that the mass is equal to 0.045 kilograms. I'm just identifying all the variables in our F equals ma. We don't know the acceleration. That's what we're trying to find. And now we have three forces. These are Y forces. We have thrust. This is the engine thrust, which we determined earlier to be 4.14 newtons based on the impulse and the time. We have gravity, which hasn't changed. It's still downward at 0.441 newtons. And we have this additional new drag force of drag. It's resisting motion. My arrow points down. I better make it negative. 0.3 newtons, I believe, was the value they gave us. Yeah, 0.3 newtons. Right, so now I have these three forces, one up, two down. They're going to sum together to cause this mass to accelerate. So I'm going to set up my second law equation, and I'm going to draw them out. I'm going to sum my forces. Thrust plus gravity plus drag. If I add them all up, that's what the sum of the forces would be. That's going to cause the mass to accelerate, right? So I have three forces on the left side. I'm going to put them into my equation with the values. I have positive 4.14. I have negative 0.441. And I have another negative, which is drag, negative 0.3. Apologize for all the sig figs. I have different number of decimals. And the mass is 0.045, and I'm solving for that unknown A value, right? So on the left side, I can start to add everything up. 4.14 minus 0.441 minus another 0.3 gives me my total imbalance or total net force, 3.39. Let's call it 3.4 upward, 0.045 A. And now I'm going to divide that by 0.045, and I get my overall acceleration of 75.5. A is equal to 75.5 meters per second squared, right? So in the real world where we have air resistance, it certainly is going to affect it. If I did not have any air resistance, this is my acceleration if there was no air. In the real world, we get drag, and it's going to lower the amount of acceleration we get over the course of that acceleration phase. So I'm going to have 75.5 as my value when I include that additional force on there, right? So here we get a bunch of scenarios where we look at this model rocket and the different forces applied to it. We see the minimum amount to get it off the ground. It just has to overcome gravity. You notice the normal force goes away. Fn is 0 at the instant it leaves off, so we don't have to worry about a normal force. There's no friction. In fact, that's what drag is. It's air friction. Right? And then we see some engine specs and how to use momentum and impulse to find the force applied over that. It's kind of like a little collision happening. And then we see what happens when we add that thrust force and gravity to figure out the total acceleration of that rocket, both theoretical and when we add a little bit of air resistance, right? So we get really good at identifying a free body diagram, what forces are on there. And then this process right here is really how you solve every dynamics problem. You start with F equals ma, the second law. You identify m, a, and any forces on there. In this case, it's a y direction problem. Everything is in the y direction. This is a one-dimensional problem, but later we're going to see some other problems where you have two dimensions, and we just organize them in x and y. But this process of then summing the forces and setting them equal to ma, And then just being mindful that these are vectors. So we're just going to include the signs with them, pluses and minus. And that's where drawing a picture with the arrows is so critical. All right, and if you do everything right, you're going to get an answer. And there's going to be a sign associated with that acceleration. We expect it to be upwards, and we get a positive answer for that acceleration. So just a really good example here. We see some basic concepts of the second law.